Hello, this is Dr. Turkawi. I'm currently an assistant professor at the Department of Anesthesiology Division of Pain Medicine at Stanford University. In this lecture, I'm going to give you an introduction to systemic review and meta-analysis. I'm going to cover the type of reviews, and we'll give you an introduction to systemic review, then to meta-analysis, and I will wrap up with some practical tips. So type of reviews. Generally speaking, we have three types of reviews. We have non-systematic, or often we call it narrative review, and we have systemic review and meta-analysis. What's the difference between them? In the narrative review, it can be non-comprehensive. It is mostly, or hopefully, qualitative review, and there is a chance of personal bias in the conclusion. In the systemic review, we should attempt to find and summarize all relevant studies, may even include unpublished data. Follows a rigorous search strategy using predefined inclusion criteria and search multiple databases. We should evaluate the quality of each study using rigorous predefined criteria. So this is an often qualitative study. In the meta-analysis, it's like systemic review. You build on that concept, plus you use statistical techniques to pool data from independent studies, and also you try to include unpublished studies. So in this type of review, usually you have a quantitative evidence synthesis, and usually you end up presenting numerical summary of the result. So let's start by systemic review. I'm not going to cover the narrative review in this lecture. It's important to know that both systemic review and meta-analysis are important work as they allow decision-making on methods, interventions, treatment, practice, or policy based on the base of available evidence. Systemic review is an attempt to objectively identify all the relevant literature with review to selecting studies based on specific criteria, collect the documents, review their contents, and critically analyze them to assess the underlying evidence. Systemic reviews must be comprehensive and based on predetermined protocol that can be reproducible. The quality of the results of the systemic review produced through the research synthesis depend on the quality of the studies and their design. Usually there is a 5 steps for systemic review. 1. Framing a research question for intended review. 2. Identify all relevant work in the published and unpublished literature. 3. Assessing the quality of the studies. And 4. Extracting and summarizing the evidence. And 5. Interpreting the findings. Before starting the study or review here, the research team need to determine and agree on reason for the study, research question, and inclusion and exclusion criteria. So the first step, as I said, the literature review. after you determine the question and you agree with the team. The team must prepare a search strategy. I highly recommend involving a librarian on this key stage, especially for beginners. Relevant databases should be searched like PubMed, Cochrane, Embase, Medline, and others, but these are the four commonly used and best, I guess, databases. Sometimes your library does not have all these databases. I had that issue before. This is not an excuse, so you cannot just say, I have seen that I'm using PubMed and Cochrane. You really need to attempt to reach out to other institutes, to friends, colleagues, and try to use their library. Look for unpublished data by finding ongoing studies. For example, you can go to clinicaltrial.gov, or what I found it frequently helpful if you check out relevant conferences and look at published abstracts. So if you found something relevant, you can reach out to the authors and see if they still have unpublished data. It's important to export the results of the database search into citation software, especially when we start to talk about meta-analysis. There are a bunch of citation software. I used Mendeley and EndNote, and a little bit Zotero. I really enjoyed Mendeley and EndNote. The search should be intended to all major languages to make sure that the publication is in non-English languages are fully covered. It is important to record the search date, to note the cutoff date up to which the review entries are included from a particular database. Reviewing the search outcome. At least 2 members of the review team should conduct independent searches in all relevant databases and resources, considering both electronic and paper version of the material, and then reconcile the information gathered independently by members of the team from the identified studies. If needed, a third reviewer may be engaged to reach agreement on the selection of any disputed studies. Any limitation or weakness of the search should be documented and included in the review report. At the first stage, the selection of studies based on checking the title of the article by the independent reviewer. The studies selected at the first stage are then critically analyzed and checked based on abstract to decide the stage of selection. The first stage, look at the title, read the abstract. The full text review is then conducted in the studies selected in the second stage. The second stage, read the full article. Thus, the identified studies could be excluded in several stages, either through the title, the abstract, full text. If you wish to call it 3 stages, title, abstract, full text, that's also possible. The list of references or bibliographies of the items selected by full text checking should be reviewed to identify any additional studies on the topic of interest. I often find this very helpful, and sometimes I find extra references in the bibliographies of some of the manuscript that I missed somehow during the pulling the data or reviewing the databases. Collection of studies and extraction of data. Data on the items of interest should be independently collected on a spreadsheet in a predetermined format. The format should allow sufficient flexibility to accommodate variation, as different authors may report the data in different format or scale or unit. Common example, pain scores. Some will report it from 0 to 10, some will report it from 0 to 100, especially in the older studies. It is a good idea to pilot the data extraction sheet with a subset of the studies. Usually I start to enter like 3 studies, then I look at the data sheet and I see if I need to expand it, add few things, modify it. Be prepared to convert some result to other format. Common examples, some studies report result on median, you need to convert it back to mean. Some studies report in standard error or confidence interval, 95% confidence interval, you need to convert it back to standard deviation. The data from independent studies should be compared item by item, and agreement should be reached between the 2 authors. Sometimes you need to contact the study's author to clarify some result. Even if the author does not respond, this should be attempted and documented. If they responded, I personally acknowledge them in the manuscript. Software are also available to help with that data documentation. Eventually, these data need to be exported to statistical example. So example here of software. So after you pilot the data, either you can continue using Excel or let's see Google spreadsheet or whatever, or you can build a data entry template on RedCap. So especially if you have a big meta-analysis, you have let's say 10 people pulling data, and RedCap is not a bad idea actually. Okay, so this algorithm from PRISMA, it's a standard way of presenting your process through identification of potential studies to screening to inclusion. And it's very important, as you see, that at any steps you write exactly how many articles you found and how many you end up with. So an example here. So this is one of the meta-analysis I published in anesthesiology in 2017. It's a big meta-analysis, as you see. So we found more than 3,000 potential resource references from 4 databases we searched, then 5 more from additional sources, as I mentioned, mostly from conferences, abstract and published data, reaching out to people that we thought that they might be doing some similar studies. And then the software kind of do that for you, remove the duplication, because it's not uncommon that PubMed and Embase, they will pull out the same studies for you. So at that stage, you can remove the duplication by using the software. Then we end up with about 2,500 references by reviewing the title and abstract excluded more than 2,000, and then end up with 437 articles that we read in more details, and we excluded a bunch of them. And here you see why we excluded them. It's important to add this information here. And then we end up with 170, and that's the final number we analyzed and included in the systemic review. Now, some people confuse this and this. So this one is what you included in the meta-analysis, but sometimes you included some data that you don't pool, you included some reference that you don't pool data from them. So that's mostly for systemic review. Level of evidence. In general, the level of evidence from primary sources are broadly categorized based on the study design as follows, from highest to lowest: experimental, like randomized or non-randomized control trials; quasi-experimental studies, such as before and after study; interrupted time series; and finally, observational studies like cohort study and case control study. Tools for assessment of quality of the study. Based on what kind of meta-analysis you are doing or systemic review, there are multiple tools. The most common, most of us familiar with, is the PRISMA, because most of the meta-analysis are systemic review actually based on clinical trials. But you end up, for example, using cohort studies or epidemiological studies, then you might use MOIS. And for non-randomized studies also, you have another tool to assess the quality of studies. Let's shift gear and talk about meta-analysis. So just so you know, I used, these are three of my published meta-analysis, and I use a lot of materials from them in this lecture. Fortunately, all these three are free access, so you can just go to the journal website and download them freely. I am adding the link for each one at the end of this lecture. But these are, you can use them. We attempted to add a lot of information on these, and as you see, there are different things about this meta-analysis. So for this example, we use mixed effect meta-analysis. Here we use meta-regression, we use trial sequential analysis. There is a lot of explanation about trial sequential analysis in this paper, and here we use network meta-analysis, and there is a lot of description of that approach specifically in this article with supplementary material, more than 170 pages. So make sure you check out the supplementary material and read the protocol. It's very helpful. Now, the term meta-analysis was invented by Glass in 1976 as a statistical procedure to reanalyze the published statistical analysis from many independent studies for the purpose of synthesizing and integrating the findings in the context of educational research. There is pros and cons to meta-analysis. Let's go through them. So the strength of meta-analysis that it provides more statistical power than the individual studies, because basically you are lumping them all. It also produces objective result, not like narrative review. is capable of combining quantitative data of every individual studies to estimate a pooled effect size, which is very cool, able to produce the synthesized pool estimate of the common effect size, even if the result of the individual studies are inconclusive or conflicting in many times. Meta-analysis based on well-conducted randomized controlled trials provide the highest level of evidence by controlling extraneous variation and bias. On the other hand, it's really vulnerable for abuse by people who are not evidence informed or sometimes ignorant, or sometimes they have ill motivate or motive. Inclusion of studies with significant bias in the meta-analysis will lead to misleading results. We see this commonly, unfortunately. The quality of the results of meta-analysis are dependent on the quality of the trials or studies included in the synthesis. So if you have poor underlying trials, there is nothing you can do about that. Unfortunately, you will end up with a poor conclusion or inconclusion from your meta-analysis. Inappropriate if there is no common underlying effect size that each of the independent studies is attempting to estimate, like mixing of different effect size measures or same measures with different scale. For example, some of the old clinical trials in anesthesiology and pain management, they used to report pain as mild, moderate, severe instead of pain scores. You cannot combine that with the newer studies that report the pain scores from 0 to 10, because here you are like combining apple and oranges. This will give you a very confusing and misleading result. Again, selection of wrong model, especially to deal with the heterogeneity, I'm going to touch base on that, will lead to misleading results. Effect size in meta-analysis, very important concept to understand. The effect size is the name given to a family of indices that measure the magnitude of treatment or intervention effect. Effect size are aggregate summary statistic. For binary or categorical outcome variables, we use proportion, relative risk, or odd ratio. For continuous outcome variables, we use standardized mean difference, weighted mean difference, and Pearson product moment correlation coefficient. Here is a useful equation for you to convert odd ratio to standardized mean difference, for example. If the raw data, individual patient data from all selected studies are available, then one could analyze the individual patient data, IPD, using what we call the mega analysis, which is one of the very good meta-analysis ways. I've seen it more and more common nowadays. A common way to represent the result of meta-analysis is via a graph called forest plot. I'm sure all of you have seen forest plot before, and I'm going to go over that and explain it in a minute. This graph shows the confidence intervals on the unknown effect size based on the estimates of the individual studies and the pooled estimate on the same chart. A forest plot contains a plot of confidence interval and effect size against the study identifier. So here is a forest plot. This guy here is the confidence interval. I'm gonna explain to you why some of them they are very wide and some of them they're very narrow. The box here, the size of the box correlate with the weighted effect of the study in the meta-analysis, basically sample size. And then you see this dark, bold, black line. This indicates the no difference line. So as you see here, risk ratio of 1, which means no difference. And then the dotted orange line here that cross the diamond in the middle, it gives you the estimate, the pooled estimate of effect size. And this is again the confidence interval of this estimate. So speaking of confidence interval, the width of the confidence interval depends on 3 factors, and this is very important things for you to understand. Confidence level, the width of the confidence interval increase as the confidence level grow larger from 90% to 95%. We often use 95%, but sometimes people can truncate that to 90%. To the sample size, the width of the confidence interval decrease as the sample size decrease. Like this example like this study, for example, then the sample variance, consequently the standard error, the width of the confidence interval increases as the sample variance increases, and we'll explain that in a minute. So when you're dealing with heterogeneity and how to control with heterogeneity in meta-analysis, you can use different models. The two commonly used models, the fixed effect model and the random effect model. There are a bunch of other newer models like the inverse variance heterogeneity model or the mixed effect model. For example, I use it in one of my papers. However, before I dig deep in heterogeneity, what's heterogeneity? So heterogeneity, any kind of variability among studies. It can be clinical, for example, different population difference, or in one of my paper, which I reference frequently in this lecture, the ondansetron effect on post-spinal anesthesia, hypotension, and bradycardia. So clinical variability, for example, in this specific situation can be simply the definition of hypotension. Different studies use different definition of hypotension. So that's called a clinical variability or clinical heterogeneity. Methodological heterogeneity, for example, dose differences. Some studies use ondansetron 4 milligram, some of them use 2 milligrams, some of them use 8 milligram. So that's methodological heterogeneity. Then statistical analysis difference. So some of them they used mean, some of them they use median, some of them they use ANOVA, some of them they use just 1 point time. So this is called statistical. So now when you read the article, you realize that, oh, there is a bunch of heterogeneity, there is a variability between these studies. So generally speaking, almost I haven't seen any single meta-analysis does not include variable trials or heterogeneity in trials. So if in that case, you would go with the random effect model. Fixed effect model, comparison between them, it's one true effect across all studies. Here you have varies between studies. Difference between studies due to sampling error only. Difference between study more than sampling error in a random effect model. Large studies more influential in effect size estimation, while in the random effect model, weight between all studies is more balanced. Here, account for within study uncertainty. Here, account for within study and between study uncertainty. Here, summary effect, common effect. Here, summary effect, mean effect. Here, null hypothesis, zero effect in every study. Here, the nine hypothesis is zero mean effect. Here, the summary effect limited to identified population, and here it's more generalizable. So again, in the fixed effect model, you mainly assume all studies are measuring the same treatment effect and estimates that one effect, if not for random sampling error, all result would be identical. While in random effect model, you assume that treatment effect varies between studies, attempt to estimate the mean of the varying effect, and uses an estimated between study variance. Now let's talk about how we assess heterogeneity. So we have a bunch of statistical tests, of course. The most common one is the I-squared statistic, which is a percentage of variability in effect estimate that is due to heterogeneity rather than chance. The larger the I-square, the more the heterogeneity. So per Cochrane classification, if your I-square between 0 to 40, that might not be important. Between 30 to 60 may represent moderate heterogeneity, and between 50 to 90 may represent substantial heterogeneity, and 75 to 100 considerable heterogeneity. So as you see, even the numbers overlap here. Second one here, another one is the Q test or chi-square statistic for heterogeneity that give you a p-value, and you look at that either significant or insignificant based on the cutoff value of 0.05. Then you can also use the Turner method, which is mainly for dichotomous outcomes. So here is the first plot from one of my meta-analysis, the one I told you about. We looked at the effect of ondansetron versus placebo in this specific first plot. It's for hypotension after spinal anesthesia. So it's one of the common side effects of spinal anesthesia that people develop hypotension within a few minutes. So the proposal was, okay, if I use ondansetron beforehand, then that should prevent or ameliorate or reduce the severity or reduce the incidence. Here we're talking about incidence in this specific first plot. Now, as you see here, this is a bunch of underlying trials that we included. I had one of them, and this is what motivated me to do this meta-analysis. So, like as you see, this is our study. We didn't find any difference whether ondansetron or placebo, while the majority of the studies they did found actually, and some of them also didn't find. Now, this is why I decided to do the meta-analysis. Now, as you see, some studies, they combined obstetric patient like C-section with general surgery. So that's clearly a clinical source of heterogeneity, because simply the mechanism of hypotension can be different between C-section with a patient with big uterus pressing on the inferior vena cava versus general surgery, which is probably pure pharmacological reason, right? So here we did subgroup analysis, and I'm gonna touch base on that. So let's look here on the result. So overall, this is the overall estimate. So you see the diamond here. It's not touching the non-benefit here, which is the risk ratio of 1. It is less than 1, which means it's protective, right? If it's more than 1, it's a causative thing. So it's less than 1, and as you see, the confidence interval doesn't include 1, which is statistically significant. So your pooled risk ratio in this example is 0.62, and that's the confidence interval. But if we look here at the heterogeneity, we have the tau square, we have the chi-square, and we have the I-square, 60%, right? And it's statistically significant. So there is a heterogeneity, and we know that, right? When we separated them and we did the C-section, we also found heterogeneity and statistically significant. When in the other surgery here, the heterogeneity is less and it's not statistically significant, and you can see the pooled estimate crossing the 1, and you have a wide confidence interval and it's not significant. Okay, so how we deal with heterogeneity? So there are 3 common ways to deal with heterogeneity. Subgroup analysis, very simple, as I showed you in the previous graph, meta-regression, and sensitivity analysis. So subgroup analysis, to group the studies based on value of a moderator, for in that case, the type of surgery. Separate meta-analysis are conducted on each of the subgroup, and this allow within subgroup result to be examined. Meta-regression is like meta-regression you do in other studies, not meta-analysis. But in meta-analysis, we call it the covariant, we call it moderator. A method that refer to using a regression method to find and account for systemic effect in size of the effect of the interest. Meta-regression is conducted by regressing the observed effect on one or multiple, that's the key here, study characteristic. In the absence of appropriate good moderator characteristic of all individual study, meta-regression would be either impossible, or ineffective. So a common example here, meta-regression, if we have a dose variation. So let's say people use ondansetron 2 mg, 4 mg, 6 mg, and 8 mg, and you know it's helpful, right? But you want to know which one of these doses is really the best. So you can use meta-regression, and you can refer back to my study that I put the reference there with the similar examples. Sensitivity analysis, I like this one, and it's very important. And classical example here, if you separate high quality studies and you just run meta-analysis on them. So let's say you have 14 trials in my ondansetron paper. Let's say 10 of them has good quality. So after I run the first analysis in 14, then I run the sensitivity in 10, and I compare the results. The most important, there is no direction difference. So one is like supportive, then when I did this, it's like, for example, not supportive. That's a big problem there. Okay, assessment of publication bias. Assessment of for a small study effect can be done both visually by drawing funnel plot and statistically by applying Eager's regression test. An asymmetric funnel plot is expected in the presence of publication bias. Publication bias is only one of the potential reasons for a small study effect. Small study effect can be observed due to real differences in the relative effectiveness observed in small and large trials. For example, if an intervention works better for severely ill patients who are more difficult to recruit, they may be overrepresented in a small trial. In this setting, we expect smaller trial to show larger effect. In this example, asymmetry is due to heterogeneity and not publication bias. To disentangle the effects of heterogeneity due to sample size and publication bias as a cause for small study effect, you can use the counter-enhanced funnel plot and a selection model that provides the correlation between the magnitude of the effect and the probability of publication. A zero correlation implies that there is no publication bias. So this is again from Ondansetron paper. This is the funnel plot here, and here we're talking about the hypotension data, not the bradycardia. So A, all studies, B, just C-section. So when you look at the funnel plot, the horizontal axis express the logarithm of the risk ratio, log RR, while the vertical axis express the inverted standardized or standard error. Notice the difference in standard error between the two graphs. As you see, we have a wider standard error when we included all the studies. You can notice there is asymmetry between two of them. You can notice there is a positive association between inverted SE and observed effect size. A regression line with standard error regressed on effect size orange color. Contour effect funnel plot in the other side here. Again, all studies and C-section. The horizontal line expresses the log RR, which is the effect size. The vertical line, the standard error. Region of statistical significance are indicated with different color, with white suggest areas of negative finding. So as you see here, there are no small negative studies or studies in white area, indicating publication bias may be the reason for small study effect, and you can clearly see asymmetry. So there is less negative studies here than positive studies. Okay, let's talk about risk of bias assessment. I highly recommend using Cochrane Collaboration's risk of bias assessment tool, which assesses the following factors. 1. Random sequence generation that reflects selection bias. 2. Allocation concealment that reflects selection bias also. 3. Blinding of participants and personnel, which reflect performance bias. 4. Blinding of outcome assessment, which reflect detection bias. 5. Incomplete outcome data, which reflect attrition bias. 6. Selective reporting, which reflect reporting bias. And finally, other bias. This is usually something the research team should determine and agreed on in priori before starting the result. Also, you can see my previous meta-analysis to see different example we used. So the end result will be a graph like this that label each factor as green, yellow, or red. Obviously, green is good, red is bad. And I also recommend to use grading of recommendation on assessment, development, and evaluation, which is simply grade. So grade, they have a very nice software which I used and I recommend. For the grade software to calculate the quality of evidence, the sample and event size, as well as the following inputs are input to the software. So study design, risk of bias, which you get it from based on the Cochrane collaboration risk of bias assessment, and usually it's either not serious, serious, or very serious. Inconsistency, widely differing estimate of the treatment, effect across individual studies, graded again as not serious, serious, and very serious. Indirectness, indirect comparison and differences in population, interventions, and outcomes of interest between the studies, graded as again serious, not serious, serious, and very serious. And then imprecision, when studies include relatively few patients and few events occur. In other words, estimates of the effect usually have a wide confidence interval that include both important benefit or no important effect. Then other considerations like publication bias, large effect defined as relative risk of more than 2 or less than 0.5 based on consistent evidence from at least 2 studies with no plausible confounders, and a very large effect as RR of more than 5 or less than 0.2 based on direct evidence with no major threats to validity. Then plausible confounding, all plausible confounding would reduce the demonstrated effect or increase it if no effect was observed, and presence of a dose response gradient. So this is where you can find the software. Okay, so based on that, the system assigns each outcome meta-analysis on the following for quality grade. High quality further research is very unlikely to change the confidence in the estimate of the effect. Moderate quality further research likely to have an important impact on the confidence in the estimate of the effect and may change the estimate. Low quality further research very likely to have an important impact on the confidence in the estimate of effect and is likely to change the estimate. Very low quality. Any estimate of effect is very uncertain. So again, this is from my ondansetron paper. You can go back to the paper to see exactly how we did that. So basically here we looked at study design, risk of bias, inconsistency, indirectness, imprecision, another consideration is that you see graded each one of them, and the software also you input the sample size, it calculates the relative risk for you and give you what does that mean. And then here it gives you the quality, which is very nicely presented here. So you can see low, very low, low, very low, very low, very low, and low. Okay, I'm going to wrap up here with a few practical steps for you. Now, how to choose a topic? This is very important because it determines the next question. As a beginner, I would recommend you work with more senior person in your field, and then you need to know what are the controversial and hot topic actually in your field. So when we did the ondansetron study, that was like a hot topic. Every few months you have a new trial saying something, and you have to help the reader and the physicians and practitioners to reach a conclusion. So that's a good topic. Then how to make sure it's publishable? First, you want to have a good topic, right? And second, you want to see if there is any published meta-analysis before. And third, you want to see if you have a good number of trials or studies to include in your meta-analysis. How to build your team. So as a general rule for me, especially when I started, you look for people who like first see what's your deficiencies, right? Okay, I don't know how to do the library search. Okay, then you need a librarian. I don't know how to do the statistic. Then you need a statistician. I don't know how to write the manuscript. Then you need someone to help you with writing the manuscript. I don't know how to choose the topic. Then, so you get the point. So look at your deficiency and build your team. Eventually, even if you know all of that, you need a team with you because you can't just do a meta-analysis by yourself. What citation software to use? I'm not gonna give you one, but as I mentioned in the previous slides, I used EndNote and Mendeley, and I like them both. EndNote, you have to pay for that. What statistical software to use? So there is a lot of available statistical. I just find this list. Like I made this list for you, but the list is way bigger. So I personally used Revman, Stata, R, and comprehensive meta-analysis. So, and sometimes you need to use more than one based on how complex your meta-analysis. So practical steps. The first step for both systemic review and meta-analysis is to establish the research team. That comprises of experts from all relevant areas, like the scientific field, the librarians, statistician, methodologists, etc. Do a quick search, check if there is similar meta-analysis done. Is there enough published studies to make a good meta-analysis? I would say at least 10. I wouldn't personally do it if it's, I would say at least 4, but I wouldn't do it if it's 4. I hope you find like at least, 7, 8, 10. The more is better. Start writing the protocol. See example of protocol template in my previous published meta-analysis. And then register your study. Please register your study in something like Prospero, which is International Prospective Register of Systemic Review. In Prospero, you actually can check if there is any ongoing similar study, and your protocol will be published, which is good, with a date, and it's permanent. Delegate responsibilities among the research group and set up time. This is very important. You want to say, okay, data extraction will take 2 months. That's the deadline. We do this. Otherwise, this will take forever. Use appropriate software. You can use software for data entry, as I said, RedCap or something like that, or you just use a spreadsheet. And then you please use Cochrane collaboration risk of bias assessment. You can use great software. This is the Prospero. This is the link for them. And here is like my final opinion or advices. Meta-analysis is not a good way to build a reputation, as it does not make you an expert in a specific area or adding novel science to the field. So, you know, I personally, again, it's up to you, but I personally don't recommend like you keep your entire career just doing meta-analysis and systemic review. It's good to do some, especially if you have a good reason for that. Frequently check there is no one else doing the same meta-analysis at the same time or just published. This minimize your chance to get your meta-analysis, this maximize. The point here, if you take like a year doing your meta-analysis, and while you are writing the manuscript, just one published, and you have the same result, most likely you will not get yours published. Only repeat a published meta-analysis if it will add substantial knowledge to the field, like change the previous conclusion. Here's my references. Here is my previous articles. And thank you for your attention. And please don't forget to subscribe, and you will see more lectures. Thank you.